Hi, this is NV Fitton, and my purpose today is to go over the quiz on rational functions that we had last week. So, this first problem we did before in class, but what the heck, let's have another look at it so that we can be sure of the method. So, I'm going to start writing down the characteristics that I see. The first one is the horizontal asymptote, which is at y equals 1. And that tells me two things. One, the degree of the numerator is the same as the degree of the denominator. And I also know that the ratio of the leading coefficients is 1. Okay. Next thing I want to make note of is the vertical asymptotes. We have 1 at x equals negative 1 and 1 at x equals 4. And that tells me that in the denominator, I have x plus 1 and x minus 4. Okay. Next, I see the points 0, 0, and 2, 0. So, what those tell me, let's see, I have zeros at x equals 0 and x equals 2. So that says that x minus 0, or just x if you like, and x minus 2 are in the numerator. So let's put all of these things together. I have this equation of x minus 0 and x minus 2 in the numerator, x plus 1, x minus 4 in the denominator, and I'm going to imagine substituting 0 in for x, and then I have 0 in the numerator, so that tells me that yeah, this guy here is definitely going to be a 0. What I really need to do here is to put this much in Desmos and see if it needs any adjusting. So here's my Desmos screen, and I went to the Tools menu here. I turned off the minor grid lines. I set the step size to be 1 for both x and y. And that's how I get this nice clean picture here. So, over on the left, I need x times x minus 2 over x plus 1 times x minus 4. And dang it, that doesn't look a whole lot like the picture that we have here. I can zoom in some. I can add asymptotes by doing things like saying y is equal to 1, x is equal to negative 1, x is equal to 4, and then I go to the setup screen to set all of these to the right colors, really trying to replicate the picture that we had on the quiz paper. And there we are. Okay. And these points I could get by just putting in their coordinates like this. But you never know just what color you're going to get when you do this. Okay, and there's our graph. Yeah, I like it. Okay, onward to the next problem. And here we have an oblique asymptote, or what our book calls a slant asymptote. And my drawing should have included this vertical asymptote here too, but I hope that you all saw it, knowing that this thing has a vertical asymptote by looking at it. Okay, so let's start writing down our observations. Oblique asymptote. And the fact that we have the oblique asymptote says that the degree of the numerator is one more than the degree of the denominator. Okay, and while we're at it, let's consider the equation of that oblique asymptote. It has a y-intercept of 0 and a slope of negative 1/3, so we can write its equation here. Y is equal to negative x over 3. And that tells us that when we finally divide the numerator by the denominator, we will have this y equals x over 3, negative x over 3, as a part of our solution there. Okay, next we have a vertical asymptote at x equals 1. So that says that we have a factor of x minus 1 in the denominator. Okay, so this is a fairly simple drawing. The fact that we have just the one vertical asymptote and this one known factor in the denominator suggests that all we need is 2 in the numerator. Okay, so the zeros of the graph at x equals negative 2 and x equals 3 say to us that we are going to have factors of x plus 2 and x minus 3 in the numerator. So let's write down that much. Oh, I forgot to say f of 0 is equal to negative 2. Okay, so I have f of x equal to, there's probably some constant here. I don't know what it is. I'm going to have to find that out in time, but meanwhile I have x plus 2 and x minus 3 over x minus 1. Okay, now if x were equal to 0, then I would have 2 times negative 3 for negative 6 over negative 1 in the denominator, which would give me a ratio of 6 here. And I don't need this 6, I need a negative 2. So I'm going to multiply the 6 that I have here I have f of 0 is equal to 6 without a scalar. Okay, so I need to divide that 6 by negative 3, or rather multiply it by negative 1/3 in order to get the negative 2 over here. So let me put that in. Negative 1/3. And now I'm going to check out this result in Desmos. So here's the picture I get without the scalar of negative 1/3 in front. let's put that in. 1, negative 1 over 3. And there we are. And I'm going to change this asymptote to positive 1. And turn it back on. And there we are. So the points that were called out were negative 2, 0, and 3, 0, and 0, negative 2. And there we are. Okay, third problem. This one is more complicated. I have, let's see, I have no horizontal asymptote. I have no oblique asymptote. So this suggests that the degree of the numerator is greater than or equal to the degree of the denominator by at least 2. Okay. Next thing that I see, I have 6 zeros. I don't think we ever had that many before. That means that each of these zeros needs to make a factor in the numerator. I'm going to have zeros at x is plus or minus 4, x at plus or minus 6, and x at plus or minus 1. We can thank Microsoft for all the smudges here with the pen. I'm real sorry about that. Vertical asymptotes. At x equals negative 2 and x equals positive 2. So that means that we know that x plus 2 and x minus 2 are factors of the denominator. But we know something more than that, which is quite interesting. We haven't seen it before very often. And that is that we have both of the, at the vertical asymptotes, we have multiplicity 2 for each of these asymptotes. We know that because the two asymptotes go up in the same direction. There and there at positive 2, and there at negative 2. So that means that not only do we have these factors of x plus 2 and x minus 2, each of them is squared. Well, that's pretty cool because I have these 6 factors in the numerator, and now I have 4 factors in the denominator. That makes a difference of 2, and that is just enough to give us this shape that is kind of like the shape of a parabola. So, let's write out this much and see how that looks. Okay, I have f of x. I'm going to leave room for a scalar. And I'll determine just what that scalar is by looking at this f of 0 equal to negative 12. I'm also going to have x plus 6, x plus 4, x plus 1, and then x minus each of these things. I'm just writing them down left to right. And then in the denominator, x plus 2 squared x minus 2 squared. So now let's think about the 0 here, f of 0 equal to negative 12. So if we plug in 0, we have positive 24 times negative 24 divided by 4 times 4. I got to turn the machine off while I figure out what the heck that is. Okay, so mentally, if not in fact, we're going to cancel, so to speak, each of the 4's with the 2's underneath. And so now we have 36. In the numerator, we have a leftover negative sign here. So we have actually negative 36 times negative 1, and then a leftover negative sign from this. So that means that f of 0 would be negative 36. Okay, we only want negative 12. So that says that again, we are going to have a 3, a scalar of 3, in the denominator, but positive this time. To save space in Desmos, I made the x minus 6, x plus 6 into x squared minus 36, and so on. But you can see that with that scalar of 3, this thing came out just like the picture that it's supposed to look like. Without the scale being perfect, but all the dots that we need here are where they're supposed to be. Okay, last problem. We have a horizontal asymptote of y equals 1. So again, that says that the degree of the numerator is the same as the degree of the denominator, and that the ratio of the leading coefficients is 1. Okay. I'm wondering, do we have some symmetry here? No, I don't think we do. Symmetry's nice, but we don't happen to have it here. Then we have vertical asymptotes at x equals negative 1, x equals positive 1. So we know that x plus 1 and x minus 1 are in the denominator. And then we have what we can only describe as funny business in the neighborhood of x equals 0. What's so funny about that? Well, two things. One, we have an insidious hole. And two, we have a shape that is a lot like x cubed. So, let's see what we can make of those. The function is not defined at x equals 0, yet we don't have a vertical asymptote there. We have the insidious hole. So that says that x minus 0 is in the denominator. And then the shape like x cubed at x equals 0 says that we have some x's in the numerator too. How many of them? I don't remember, to tell you the truth, but I think it's going to be 3 of them. Let's see what we have here so far. F of x, leave room for a scalar. Let's see. We have x plus 1, x minus 1, and also x minus 0 in the denominator. I forgot to mention this 0 here. We have x minus 2 in the numerator to get that 0 there. Also, we know that f of negative 2 is equal to 8/3. That's going to come in handy somewhere. Okay, and so far I have x minus 2. If I put an x to the 3rd power here, then I'm going to need another 0 there. I'm going to need another 0 in the denominator in order to make the 2 of these of even size. So let's try making that one squared. And where does this get us? If x is equal to 0, then I have a negative 2 over negative 1. I'm going to need a lot more than that. But let's try this much in decimals. I gotta tell you, this one came out a lot better than I expected it to. Why? Well, I think I was getting a little bit confused when I thought of this 8/3 up here. How was I going to get that? I'm not getting that by plugging in 2 or 0. I'm getting it by plugging in negative 2. So that gets me, whatever it gets me here, I'm going to just accept it. This insidious hole didn't get there all by itself. I mean, it's in there, right? It's not going to show up on the graph unless you make it show up, as I did over here by choosing an empty hole-shaped dot. But that's it. So here is our solution for the final problem. That's the end. Thanks for your attention.